Let's say that I said, write the electron configuration for lithium. All right, cool, no problem. So lithium is a group 1a metal. Its atomic number is 3. And then if that means 3 protons, and assuming this is neutral lithium, which it is, that would be 3 electrons total. And when you put the electrons in, you always start at the bottom of the Aufbau diagram and move your way up. So 1s2 would be the first part. And remember, 1s's and 2s's and 3s's can only hold a maximum of 2. So once the 1s is filled, the third electron in lithium would go in the next one, 2s1. So 1s2, 2s1 would be the electron configuration for lithium. And notice that if you take those superscripts and you add them together, that should equal the total electrons. So 2 plus 1 equals 3. That's a nice way to kind of check yourself. Now, in terms of orbital box notation, you can write this way: 1s at the bottom, 2s by itself. There's one orbital for each of the s orbitals, so that's why there's one box. On the other hand, the p's, the 2p and the 3p, there were 3 orbitals possible, so that's why they get 3 blocks. But again, 1s2, you've got an up and a down in the 1s, so that house is filled, but 2s has just a single electron in it. And you can write it up or down, it doesn't matter, but the important part is that up or down doesn't have the corresponding arrow in it. So lithium is actually a paramagnetic atom. It has an odd electron, an electron with an up without a down, or if you want a down without an up. Most chemists will write up first and down second, but really it doesn't matter. There's an odd electron running around, and that makes lithium paramagnetic. Beryllium is the next one. Atomic number 4, 4 electrons total. Always start with the 1s, so 1s2 fills that up, 2s2 fills that one up, 4 electrons total. So notice how we're literally starting at the bottom and moving our way up. Remember, s's can only hold 2, p's will hold 6, but in this case we filled up both 1s and 2s, 4 total electrons. If you do the orbital box for this one, 1s2 and 2s2 are both filled. Notice here how the ups, each up has a down, or each down has an up. Beryllium is a diamagnetic metal. It is not attracted to magnetic fields. So lithium does have a paramagnetic effect. Beryllium, on the other hand, does not. The s's are filled, each up has a down, no attraction. Boron is the next one, atomic number 5, so that's 5 electrons in the neutral atom. And like before, we're going to start with 1s and keep working up. So just like beryllium had 1s2, 2s2, the first 4 electrons, boron will also be 1s2, 2s2, but it has a 5th electron, and the next one to get filled in is the 2p. So boron, 1s2, 2s2, 2p1. This is our first p element that we've seen. So the orbital box notation, we would have 1 electron in that 2p. It does not matter which of the 3 boxes you write it in. People usually will do left to right, but it doesn't really matter. The goal is just to put it in there somewhere. And because there's an odd electron, that makes boron paramagnetic. So lithium paramagnetic, beryllium diamagnetic, boron paramagnetic. Carbon is the next one, just one past boron. It has 6 electrons total, atomic number 6. So like boron, it's going to start with 1s2, 2s2, and it has 2 more electrons to go outside of that. So that's going to be a 2p2. But there's a little bit of a twist here, because there's different ways you could put the 2 electrons in the 2p. So as an example, you could have, remember that the 2p's have 3 orbitals to them. You could put 1 electron by itself in the first one and 1 electron by itself in the second one, which would make it paramagnetic. But you could also put both electrons in the same box like that, making it diamagnetic. So what we're running into here is something called Hund's rule. And Hund's rule, there's the picture of Hund, basically realized that electrons wish to be be in their own orbital first and only pair them up after there's no more room. So for this problem, what that means, carbon will not have the paired electrons like I drew right there. It's going to look something like this. And that's what we're seeing right there. I use the analogy of if you've ever lived in a house with like a brother and sister, and if there wasn't room, like you could share a room with your brother and sister. It's not impossible, but it's awkward. Like if you want to put a poster up of a rock band and they like country music, then it's kind of awkward, okay? It's better to have your own room, but it's totally possible, all right? Well, electrons are kind of the same way. Electrons would prefer to have their own room if possible, but they can pair up, be in the same room if they need to. There's a little bit of an energy of putting two negative electrons in the same orbital, the same basic space around the atom. So Hund's rule is basically a way to minimize the energy of it. Hund's rule again just says put electrons in their own orbital whenever possible and only start pairing once there's no more room. So carbon is paramagnetic. It is not diamagnetic, even though you could draw it that way. A diamagnetic carbon would take more energy than a paramagnetic carbon, thanks to Hund's rule. Nitrogen has one more electron than carbon, so it's 1s2, 2s2, 2p3, 7 total electrons. And again, remembering Hund's rule, each electron goes in its own room until there's no more rooms possible, so nitrogen's definitely going to be paramagnetic. You can see there the 2p3, each electron in its own room. Each electron has its own space. They can put up their own posters in their room, whatever you want to say. Nitrogen, paramagnetic. However, the next one, a little bit more interesting. Oxygen, one more electron than nitrogen, all right? So just adding one more electron, 1s2, 2s2, 2p4. Remember that p's hold up to 6, so we still got some room, 8 total electrons possible. However, at this point now, that the extra electron, the 8th electron, you have to put it in with something that's already there. So in this case, the 2p system, one of the orbitals does have both an up and a down electron. The other two electrons are still by themselves, but in this case, there is no more room in the in, if you will. The electrons have to start pairing up. So one of the orbitals is diamagnetic, if you will, while the other two orbitals in 2p are paramagnetic. So oxygen is paramagnetic, like we saw. Fluorine has one more electron than oxygen, 1s2, 2s2, 2p5. Remember, p's go up to 6, so we still got some room. 9 total electrons. We're going to pair one more of those electrons. There's the orbital box diagram showing the 2p5 part. Fluorine definitely paramagnetic. Neon, which finishes off this row, has 10 electrons total, 1s2, 2s2, 2p6. And at this point now, we've added up electrons to all the downs. So every up has a down electron. Neon is a diamagnetic element. We've reached the end of the second period. The second shell is totally filled. And all of the elements in group 8A, we're going to see, and this includes helium too, by the way, have diamagnetic shells. There's no more room left. Notice too that most of the atoms we've seen have been paramagnetic. So if you have to guess if an atom is paramagnetic or diamagnetic, you should probably guess paramagnetic. The ones on the ends of the shells, like neon here or beryllium, are going to be diamagnetic, but most of them are paramagnetic, at least in their raw form. So this is kind of an overview of what we just saw of boron through neon. And again, the first ones were all very paramagnetic. Hund's rule says don't pair them up, all right? But you do start pairing when you get to oxygen. It takes less energy to put a 2p electron in as a paired electron than it does to do the 3s that we'll look at here in a little bit. So again, all of them are paramagnetic except for neon, which is kind of cool. Sodium, group 1A again, but 11 electrons total. So for this one, we're going to have just one more electron than we did for neon. So it's going to be 1s2, 2s2, 2p, thanks for playing, 1s2, 2s2, 2p6, 3s1. Or you can probably tell that it takes more and more syllables to talk about these electron configurations. So the 1s2, 2s2, 2p6 is really nothing more than neon with a 3s1 on top of it. So I'm going to introduce at this point what's called noble gas notation. And if you want to use noble gas notation, you can absolutely use it. If you're going to use noble gas notation, you must use square brackets. The noble gas goes in the square brackets, and what goes past the noble gas goes outside. So instead of saying 1s2, 2s2, 2p6, 3s1, you can say a neon core 3s1, and that's obviously less writing, less syllables when you're talking about things and stuff like that. So noble gas notation can be super helpful. Another thing that's interesting, all group 1A elements have a core neon, a noble gas core NS1 configuration. We saw lithium earlier was 1s2, 2s1. So lithium is really like a helium 2s1 configuration, and you can see here how sodium is a neon 3s2. Potassium, right below it, if you want, you can look at this, is argon 4s1. So notice how N is changing. 2, 3, 4. That number comes from the period number. If you look just to the left, that's the N number. This is kind of a cool way to figure it out. This also explains why all of the alkali metals, which is group 1A, why they all have similar reactivity. That one electron on the outside is ready to rock and roll. The number of N does change with the noble gas, but it's got some kind of noble gas inside, and then you've got that extra electron on the outside. Pretty cool. Aluminum, we're skipping magnesium. Aluminum has 13 electrons total, so it's got the 1s2, 2s2, 2p6, 3s2, 3p1, or you can just write noble gas notation, highly recommended, neon in brackets, 3s2, 3p1, which I recommend, paramagnetic, all that kind of stuff. Here's the electron configuration, what it looks like. 3p1 is all by itself. All of aluminum has the aluminum group, the twisted metals, has some kind of a core NS2 NP1. Now, some of them have some d electrons. We'll see that here in a little bit. So it doesn't work quite as well for the twisted metals as it does the alkali metals, but it is kind of a nice pattern to see. This is why a lot of the groups have really similar patterns of reactivity due to their similar electron configurations. Phosphorus, group 5A, 15 electrons total, 1s2, 2s2, 2p6, 3s2, 3p3, or neon 3s2, 3p3, which is highly recommended. 3p3 means there's 3 individual electrons because of Hund's rule once again, so very paramagnetic. All of the pnictogen group 5A elements have some kind of a core, NS2, NP3. Some of them will have some d electrons. I'm warning you about that. We'll see that in a little bit, but they do have similar outer electrons. That's why their reactivity is also similar. Chlorine's electron configuration is one of these right here. And the question is, which one is it? And that's a really good question. There's a couple of ways to answer this question. First of all, you can just look on the periodic table. Chlorine is number 17. And if you add up the number of electrons in the superscripts, you want to look for one that has a 17, all right? And I think that the only one that does that is B in this list. So if you add up the 2, 2, 6, 3, 5, that actually comes out to be 17, and that would be one way to answer this question. A second way to answer this question, you know that chlorine has 17 electrons because of the periodic table. You could follow the Aufbau diagram through 3s2, 3p5. That would be another way to confirm the answer B is correct. And yet another way is that chlorine is part of the P block of elements. The 6 columns on the right of the periodic table are all called the P block. It's the second set of P electrons. The third period would be 3p, and your 5 electrons into it. So for example, argon to the right would be a 3p6, sulfur to the left would be 3p4. Anyway, any of these ways you can figure out then the answer B is the correct configuration, 3s2, 3p5. Remember that 3s's can only have 2, so that one's not going to fly. The other ones I think are at least okay. 1s2, 2s2, 2p6, 3s2, 3p6. Answer D would be argon. E would be calcium. C, 1s2, 2s2, 2p5. That would be fluorine. The S blocks, P blocks, D blocks, F blocks can be really helpful. And we're going to talk about the Ds and the Fs here pretty soon. But for the S's and the P's so far, it makes it really easy. And again, reactivity of electrons and elements is a lot of times dependent on where you are in the different groups. So knowing that the S's are the 2 blocks on the left. And by the way, helium here should be an S block. That's an incorrect animation. But anyway, the right 6, not including helium, P block. The middle ones there are the Ds, and the Fs are the lanthanides and actinides at the bottom. Transition metals, the ones in the middle of the periodic table, are the ones that have the Ds. And if you use an Aufbau diagram, or if you just figure it out, the D electrons pop in after the S ones. And we talked about earlier how 4s gets filled in before 3d. So transition metals have some kind of noble gas core, and then there's a period number, so like 4s2, and then n-1 means 3. So, for example, if you wanted to know the electron configuration of titanium, Ti number 22, it has an argon core, it has a 4s2, and the n comes from the period number, which is 4, to the number to the left of that whole group, and then n-1, 4 minus 1 would be 3. And titanium is the second of the transition metals in that period, so that would be a little Y value number of electrons of 2. We're going to see that the D electrons are really important for transition metals. So sometimes transition metals are called D block elements because it's the D electrons which affects a lot of their reactivity. But for right now, just realize that they all have some kind of noble gas core. They're going to have some S electrons put in first, and then after that, they're going to have Ds. But the S's and the Ds, there's this n-1 dependence on the Ds. All right, it's 1 less than the S's. Here's just some examples. Potassium, 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, or argon 4s1, and that's obviously a lot easier. Calcium, 1 more electron than potassium, would have an argon 4s2, and that's not too bad. Now, scandium is the first of the transition metals. It's in the 4th period, and 4 minus 1 means it's going to be filling in the 3d electrons. So notice there, scandium would be a lot like calcium, argon 4s2, but with a 3d1. Remember, Ds can go up to 10. All right, so there's 10 possible spaces, and if you count from scandium Sc over to zinc Zn, you'll see that there are 10 elements corresponding to the 10 3d elements. Titanium, we talked about earlier, argon 4s2, 3d2. The next one is vanadium, argon 4s2, 3d3. Now, chromium, you would expect, would be argon 4s2, 3d4. But for some reason, and even I don't know, and scientists don't know, one of the s orbitals, electrons, jumps ship, and it goes from a 4s2, 3d4 to a 4s1, 3d5. This is a break in the n plus L rule, and chromium is the first exception to our rule. So I point this out because I want you to know that science hasn't figured everything out yet. All right, it should be 4s2, 3d4 according to theory. In reality, it's 4s1, 3d5. I'm also pointing this out because all I really expect you to do in the Chem 200 series is to be able to predict electron configurations based on the n plus L rule. So if you put down for chromium argon 4s2, 3d4, I would give you credit for it. The actual electron configuration, argon 4s1, 3d5, maybe one day I'll talk about the theory developed by you that explains why this is 4s1, 3d5 and not 4s2, 3d4. But anyway, what are you going to do? Moving on, manganese, argon 4s2, 3d5. Copper, skipping some here. Copper is another exception to the rules. It's argon 4s1, 3d10 instead of argon 4s2, 3d9. And again, it's kind of an unknown mechanism. Just realize that these ones in red here, chromium and copper, are exceptions to the N plus L rule. And there are other ones too. As you get further down, the transition metals, lanthanides and actinides, there are some exceptions. I don't understand why, but it gives you 2 chances to be right. So, woohoo, score. Anyway, trying to make up for a scientific lack of knowledge. I know it's kind of silly, but anyway, hopefully you get the idea. Exceptions, obviously, and stuff here to what's going on, 2 chances to win. So, for example, for chromium, I would expect you probably to just put down argon 4s2, 3d4, but if you put down the actual configuration, argon 4s1, 3d5, awesome, I'd give you credit for both. And the same for copper. Copper should be 4s2, 3d9 officially, but for whatever reason, it's argon 4s1, 3d10. And again, there are other exceptions on top of this. You'll see it in the textbook and stuff like that. Chromium, copper, and other elements don't follow the N plus L filling order, which drives me crazy as the instructor, but welcome to science. We don't always have everything figured out. People think it's instability associated with the D subshells. Maybe it is, maybe it's not. All I'd really like you to know is how to fill things in by the N plus L rule, and just realize there are some anomalies. And again, if you give me the answer, either the actual answer or the real answer, you're good to go. Lanthanides and actinides are similar to transition metals, only lanthanides and actinides, you're actually filling in the F electrons. So like we saw with the transition metals, the D block elements, you can find the N, the shell number, from the period, which goes left to right, and then N minus 1 was how you found the Ds. So for example, titanium we saw had an argon core, it was 4s2, and then N minus 1 would be 3d2 in titanium's case. Well, with lanthanides and actinides, you do the same kind of thing, but it's N minus 2. So if the period number was, say, 6, you would go 6 minus 2 to see that it was a 4F element you were filling in. There's 4 Fs for lanthanides and 5 Fs for actinides. We're not going to focus as much on the lanthanides and actinides. There are quite a few exceptions to N plus L rule, just showing here what is weird. There's cerium and uranium as examples of how this stuff all works out. Lanthanides and actinides are pretty cool. There's a lot of neat chemistry going on there. And again, you can find the electron configurations after this class. It's just that we're going to focus more on the transition metals and the main group metals and nonmetals. This is, again, the electron configuration filling order. It's based on the Aufbau. Notice in the lower right-hand corner here, this is basically the periodic table telling you which ones you fill in. So 1s, as we saw, always first, 2s, and then follow the arrows to 2p, 3s, follow the arrows to 3p, 4s first, here's 3d, so 4 minus 1 is 3. Notice here how the period numbers 1, 2, 3, 4, 5, 6, 7, etc., etc. So 3d and then 4p follows, then 5s, N minus 1, 4d, 5p, then you go 6s, and then notice here how here's the first 4f, it's 6 minus 2 or 4f, then 5d, 6p, etc., etc. So this is an alternative way to see how the electrons get filled in as you go through. Here's just some things you can check yourself. If you'd like to pause them before I give you the answer, that's fantastic. But I'd like you to figure out, for example, the electron configuration for iron. And I would use noble gas notation just because it gets kind of crazy. Iron has an argon core, 4s2, 3d6. Cool. Now, zinc is in the same line as iron, so it's going to look similar to iron, but it will have more 3d electrons. At the end of the zinc line, that's the end of the 3d region, so that's going to have an argon 4s2, 3d10. All of the ones there in the zinc family are going to have a d10. So zinc was 3d10. Under it is cadmium. That would be a 4d10. Mercury under that, 5d10, etc. cetera, et cetera. Technetium is on the next row down, so it's going to have a different noble gas notation. It's going to be krypton, 5s2, and n-1 would be 4d, 4d5. And then niobium, Mb, if you keep going down, that's also a krypton, 5s2, 4d3. Osmium is on the next line down, so that's going to have a different noble gas. That's going to be xenon. Xenon, 6s2. Notice the 4f14. 4f always comes before the 5ds, at least for us right now. So 4f14 and then 5d6. And then finally, one of the brand new ones, Mitnarium, which is number 109. A heroine of mine, Lisa Mittner. We'll talk about her in Chem 222. Anyway, her configuration, or Mitnarium's configuration, would have a radon core, 7s2, 5f14, 67. And again, all I expect you to know is the expected N plus L rule. There are probably exceptions for some of these, but you just have to know the given ones and stuff. If you do report the actual configurations, that's awesome too. 2 ways to win.